Okay, I'm back again. Sorry, I didn't mean to cut myself off and end the video. I also didn't mean to do the calculations in the wrong order. A squared is going to be -1, 0, 0, -1. And a cubed is -1, 0, 0, -1. If I think I did, I did that. Actually, I did this. I did it right the first time. This was a squared, a cubed. A cubed is 0, -1, 1, 0. And then a the fourth is 1, 0, 0, 1. Sorry, I was distracted by everything. So in this case, we see that a squared is equal to the opposite of the identity matrix, I2. And in this case, a to the fourth is precisely equal to the identity matrix. And we're going to see maybe later on we can see that there's kind of, this matrix is A is kind of like the analog of the square root of -1, where 1, you know, where it doesn't make any sense to say that this is equal to 1, but it's 1 in the sense that it's the multiplicative identity. I should say maybe right here that in general a times I is the same as a, and that's also the same as I times a. So this is, as long as a and I have the same dimensions, this is true, and that's why the identity matrix acts as an identity element. We'll get into more of that in the next section. So one way, why do we have this nice complicated math, this multiplication? Why can't we just multiply the corresponding entries? Well, the reason why one reason is that we can now write this. We can represent a system of equations as a single matrix equation, because we can see this first row here is really the dot product of 2, -3, and 4 with x, y, z, and the second row is the dot product of 1, 0, and 5 with x, y, and z, and so on. And that's exactly what we get if we just multiply this here we have a 3 by 3 matrix, and here we have a 3 by 1 matrix. So this makes sense. We got 2x plus -3y plus 4z equals 1, which is exactly this equation. Okay, so we can actually represent this if we call this matrix A, and we represent this matrix X, and call this matrix or this column vector B. What we now have is sort of like the matrix analog of a nice linear equation. It's a linear matrix equation, it's just AX equals B. Now that's kind of nice, and we're going to see that there's actually, we don't have really matrix division so much as we have multiplicative inverses of matrices. We can't always divide by this matrix A and find what X is. But we're going to see in some cases we can, only we don't call it division. We're going to talk about inverses of matrices a little bit later. Okay, but this is one reason we can represent every system of linear equations corresponds to a matrix equation like this. Another reason why we do this is that there is we're jumping ahead of ourselves a little bit here, but if we can define two functions going from R2 to R2, which sends xy to y minus x. This first actually corresponds to a rotation through 90 degrees clockwise. And then g of x, she sends the column vector xy to x2y. And if we were to compose this here, f of g of xy, well, this is the same as f of g of xy. Okay, well, we're going to see that notice that this matrix here, this y minus x, is actually, can be represented as the product of 0, 1, -1, 0 times xy. And this matrix, this output here, can be represented as the product of 1, 0, 2, 0, 2 xy. Okay. Now, not all functions behave like this, but these two functions can be defined in terms of matrices. So we're just sort of taking out something and multiplying it by a matrix on the left side. So this would be f of g. So this would be f of 1002 xy, and f takes whatever it's given and multiplies it by 0, 1, negative 1, 0. And if we compute this, take the product of this, we get 0 plus 0, 0 to negative 1, and 0. And this is going to be, so this is going to be 2y and minus x. And this is actually exactly the composition of what we were going to get if we were just to do it the old-fashioned way and compose these two. So this is a composition of functions is really going to correspond to the products of matrices. Might seem a little strange, but it'll hopefully make more sense when we talk about linear transformations. All right. Okay. Last thing is we'd like to talk about one more operation, and that's a transpose of a matrix. This is a very simple operation where we just take the rows and the columns and interchange them. So with if A is an m by n matrix, then the transpose of A, we denote by AT, is just the n by m matrix in which the ith column of A transpose is the ith row of A. So in this case, the ij entry of A is the ji entry of A transpose and vice versa. So this would be, the transpose would be 1, 2, 3, and this would be 4, 5, and 6. This is the first row, so this becomes the first column. The second row becomes the second column. Here we have a transpose of the 2 by 2 matrix. This would be 6, 4, and negative 1, 2. You'll notice that in this case, if you have a square matrix, the diagonal elements are the same. The elements on the diagonal are fixed, if you think about that. Here we have, here A and B are both 1 by 2 matrices. And normally we would not be able to, we can't multiply A times B, but in this case we can multiply it. B transpose is a 2 by 1. So this is a 1 by 2 times a 2 by 1. And now we can do this. Okay, and by the way, this T here just applies to the B, not the A. So we're really multiplying A times B transpose. And what's that going to be? It's 1, 2, 4 times 3, 5, 6. This is a 1 by 2. This is a 2 by 1. And so the result is just going to be a 1 by 1 matrix. We're really just taking the dot product of this row and this column, which is 3 plus 10 plus 24. Okay, 3 plus 10 is 13. 13 plus 24 is 37, I hope. Okay. 24 plus 34, 37. Okay. It's our 1 by 1 matrix. So that's a transpose. And then a square matrix is symmetric if A is equal to A transpose. So basically the diagonal acts as a mirror. Okay. And that's exactly what happens here. So it's a symmetric, for example, this entry and this entry, this is the 1, 2 entry, and this is the 2, 1 entry, and they're the same. Okay, this is the 1, 3 entry, this is the 3, 1 entry, they're the same, and so on. So matrices, we're going to see that symmetric matrices have some very nice properties when we talk about eigenvalues and diagonalizing matrices and stuff like that. All right, so next time we're going to talk about some more properties of the transpose, properties of addition and multiplication, and that will be the next lecture. Thank you.